All right, well, good morning, everyone. How's everybody doing today? Doing all right? Okay, so well done for making it in. Hopefully the weather might pick up a bit later in the afternoon. How did everybody get on with the labs on Wednesday? Did you guys like the labs? Yeah, it's pretty fun, right? And who got some measurements for the acceleration due to gravity? Yeah, okay, great. So it's a real classic physics experiment, and it's great that you guys all got, in the lab, got hands-on with this, saw how that oscillating pendulum works in practice, because today we're going to be focusing on some of the physics behind, the oscillating pendulum. But as we kind of hinted at the end of the last lecture, this is a hugely important topic in physics. It just comes up again and again and again all over the place. Now, usually when we start a lecture, I like to start by sharing with you guys why the concept is so important and some applications and examples, and then we can get into the details of the math, see how it works, okay? Now, today we're actually going to do it the other way around. So we are going to find out why simple harmonic motion is so important, why it comes up over and over again. But we can't really do that until we've understood some of the math behind, some of what goes into making it work. So for today, we're actually going to slightly dive into the math and thinking about what's going on. And then we're going to see towards the end of the lecture why it's also important. So you'll just have to take it on credit for the time being that this is super, super important, and we'll see how it works towards the end of the lecture. So just to pick things up a bit from last time, let's take a look where we got up to last time. We had this situation, we were thinking about circular motion last time. We had this object going in a circle. And then if we just looked at one axis here of the position versus time, we get this nice cosine. And then we saw last time that if we're just looking at this axis, there's this relationship between the acceleration and the position. So we get the acceleration here, and it's like a minus cosine. So we've got this relationship between the two. And we just saw this equation at the last time from thinking about circular motion. And, we said that that's what we call simple harmonic motion. Now, I suppose when we think about simple harmonic motion, the simple there, that's slightly subjective, okay? It's definitely something oscillating backwards and forwards. I guess you guys can make your own minds up at the end of the lecture if you think it's simple or not. Now, if we look at this equation here, so the relationship between the acceleration and that displacement here, we saw this exact equation for the first time last week. But you might be able to recognize that we have actually seen an equation very much of this form previously. So what I'd like to start by thinking about today is where have we seen an equation of motion of this form before? So remember, an equation of motion, it's just any equation where we have some relationship between the motion of the body. So here we've got this connection between the displacement s and the acceleration. Now you might think, well, we've not seen the omega before and the omega squared, and all this is kind of new. So, obviously some of that is new, but what we're thinking about here is the form of this relationship. And it's actually come up in one of these laws here. So have a think about this, maybe have a chat with the people around you, have a think, which of these laws have we seen an equation motion of this form before? Now, maybe you can recognize straight away where we've seen this before. Maybe you can eliminate some because they're not of this form. Maybe you can kind of recap some of the things we've seen before, have a chat with the people around you, see which one of these is going to be that form of the equation of motion. All right, then, well, let's have a look. Let's see which law everybody thinks this is. Okay, so nobody's going for Ohm's law or Coulomb's law. Okay, this is interesting. Looks like we've actually got a majority vote for Hooke's law, for Gauss's law. Okay, very interesting. So what's our thinking here? Who's thinking could be maybe Gauss's law? What do we reckon here? Okay, what are we thinking about this? Why it could be Gauss's law?
Well, I just sort of eliminated the rest of them.
Okay, so we're thinking, I guess it's not Ohm's law, it's not V equals IR, we don't think. Coulomb's law, not so much. Okay, yes, so sometimes that can be a good approach. Maybe you can eliminate a couple, only have a couple left. And what about, because we're kind of pretty evenly, what about option C? Who was just thinking could be Hooke's law? Yeah.
I think it's C because the motion at which the mass across the spring bounces seems to me like a simple harmonic motion.
Right, exactly. Okay, so we had this case, with Hooke's law, we have a mass on a spring. We're going to see that's actually an example of simple harmonic motion. So the correct answer is actually Hooke's law. Okay, so very well done, everybody who gave this question, especially if you got that it's Hooke's law. Now, this might not seem immediately obvious, right? We got the omega, we didn't see that with Hooke's law. So what we're going to think about is what's the connection here between this equation we got from the circular stuff and Hooke's law. So let's have a bit of a think about this. Let's have a think about what is going on here. Okay, so let's recap what we had with Hooke's law. So with a mass on a spring, we had that force is equal to minus kx. So let's have a think with this. So just starting to work with this equation, rearrange it a bit. With Hooke's law, how is the acceleration related to the other properties of this mass on a spring? With this question, we're really just doing a bit of algebra, doing a bit of rearranging here. So we know from Hooke's law, force is equal to minus kx, but also for any mass, any acceleration, we always know Newton's second law applies. So we always have force is equal to mass times acceleration. So we can use this, solve what's going to be the acceleration for our mass on a spring. All right, then, well, let's see what everybody thinks for this one. Okay, so thank you for pointing out. Okay, so obviously B and D are both the same. So I need to get more creative when I'm thinking up alternatives for what the incorrect answer is. And I guess that kind of gives the game away a bit, right? Because we know it has to be one of either B or D. Okay, so very well done, everybody who's going for that. Now, I genuinely can't remember which one of these is the correct answer. So let's take a look here. What have we got? Oh, okay, so it's D, but they're both correct. Okay, so whether you went for B or D, that's the correct option there. So we're really just setting those two forces equal. We solve the acceleration. We get acceleration is minus k over m. And for next time, I'll think of something a bit more interesting to spice that question up a bit. But very well done, everybody, with that. So that's what we get with Hooke's law. So that's the equation of motion that we get for a mass on a spring. And hopefully this might start to look a bit more like, what we saw with that simple harmonic motion. So let's try and think about this a bit more. Okay, so, for Hooke's law, we do the rearranging. Our acceleration is minus k over m times x. And then for simple harmonic motion, for any kind of thing that we call simple harmonic motion, so it doesn't have to be a mass on a spring, just anything oscillating, our acceleration is minus omega squared x. So we can start to see how both equations have the same functional form. Even over here we've got a omega squared, and over there we've got a k over m. So in this question, let's see, for this case of a mass on a spring, how can we relate this angular frequency to those properties of the mass on a spring? So with this one, again, we're just doing a bit of algebra. We know that they're both a times something gives us the position. So we can relate that angular frequency to that k over m and see what we get for the angular frequency. All right, then let's take a look. How can we relate this angular frequency of our mass on a spring to the spring constant and what the mass is? Let's take a look here. Okay, so what do people think? Okay, so no one's going for A and D. Looks like people are thinking it could be B or C. So the key thing is that both equations have this same form. So we know that this omega squared has to equal the k over m. So then, we just take the square root, and what do we get here? We get the omega is equal square root of k over m. So very well done, everybody, with that question, okay? Now, this is quite a useful result because it gives us some idea of how fast our mass on a spring is going to oscillate, if we know what the mass is and if we know what the spring constant is. Now, this is especially useful, for the engineers, if you're designing, like a classic example, it's like the suspension on a car or something, because maybe you know what the mass of the car is and you don't want the car to be oscillating around all over the place. So you want to think, okay, how stiff do I want to make the springs of the suspension to give the car a nice ride? That's a kind of classic example of where we might see this. Now, this is a relationship between these properties and the angular frequency. Now, we've only just seen angular frequency. Sometimes I still find, it makes more sense to think about this, in terms of just the regular frequency or the time period. So just in this question for now, let's do a bit of rearranging here. So we've got this relationship between our angular frequency and the spring constant and the mass. And we know angular frequency. So remember, it's just frequency times 2 pi. And frequency is just 1 over the time period. So let's put these pieces of the puzzle together, see what are we going to get for the relationship between the time period and these properties of our spring. With this question, so it's just a bit of algebra. We're just setting the angular frequency is equal to 2 pi f. We know frequency is 1 over time, and then we're solving for time. So put those pieces together, bit of rearranging there, work through the algebra, see what you get for the time period, how it's related to those things in the spring constant. All right, very good to see those answers coming in. Let's see what everybody thinks for this one. What's the time period for this spring there? Okay, so looks like nobody's going for D. Some people going for C. Some people going for A. Okay, so the thing with this, so remember, so frequency, it's just F is equal to 1 over T. That's the relationship. So when you do that substitution, put the math together, what we actually get is option B there. Okay, so we get T is 2 pi m over. Okay, very easy to kind of just get something a little back to front. Okay, so don't worry too much about that. What I would suggest though is it does just make your life easier. Don't skip any steps of the algebra. Just write everything out line by line. If you want to multiply things by both sides, take up plenty of space in your notes. Write everything out. And then, we get this relationship for T, okay? So very well done everybody who gave that question a go, especially if you got option B. But, the main thing, having a go at the question, it's not a big deal if you don't get exactly the right thing, okay? So that's actually what we call, simple harmonic motion with a mass on a spring. And that's a real classic example of where we see simple harmonic motion. And it comes up again and again. And that's the kind of basic physics of what's going on. Now, the other classic archetypal example of simple harmonic motion, you guys have already seen in the lab with the oscillating pendulum. Now, we saw the equation of the kind of relationship for the time period of the pendulum. So what we're going to think about a bit today is where does that equation come from? What's some of the physics going on there? So let's just remind ourselves of that situation that you guys were looking at in the lab. So, we've got our mass, we've got our spring, and we set it on a small oscillation. That's what everybody was looking at on Wednesday. And, we know the length of the string, and there's some angle that we're taking it to. And then we might say that there's some distance over here. So how far has the mass been displaced? Now, we know that if we move the mass, there's going to be gravity, pulling the mass back to where it was. So that's going to give us what we call our restoring force. And it's always pushing things back towards the lowest point, so back towards the center. Now, we know it's the force of gravity, so it's going to depend on the mass and the acceleration due to gravity. But it's also going to depend on how far we've displaced our mass. So what we actually get for the restoring force is that the force is equal to just that regular force of gravity, so mass times the acceleration due to gravity. And then we get this sine theta here, so the sine of this angle here, just because if the mass is sitting down here and our theta is equal to 0, there's no restoring force. I mean, it's still being pulled down by gravity, but it's not being pushed or pulled sideways. Whereas if we take the mass and pull it over here, then gravity is going to want to push it back to where it was. So that's just where the sine theta is coming from. Yeah.
Why is the mass negative?
Ah, great question. So why is the mass negative? So I guess it might help if I put like a space in there. Okay. So do you have any thoughts about that? Why is there a minus sign? That's a really good question, actually. Yeah.
Going up against gravity, so it's like in the opposite direction.
Yeah, that's exactly the right kind of lines there. So if we increase our S, so we're going in the direction of positive S, the force is always going to be back opposite from where we came from. So the force, the direction of the force is always opposite. So it's not like the mass that's negative, it's actually the sine theta that's negative. Yeah, but thank you for asking. That's a really good question and a really good point. So it's the same idea as with the Hooke's law with the spring constant. It's the minus k because the spring is always pushing it back to its equilibrium point. And then if you imagine, suppose we take the mass over this side, then the force is still going to be pushing us back towards the center. Yeah, so we can actually simplify this a bit. If we're thinking about small angles here, so I've got this little asterisk here, and the asterisk is if we're thinking about small angles, we can make our life a bit simpler here, because if we think about a bit of geometry here, so sine theta, that's this ratio of our displacement to the length of the string. And then that makes our life a lot easier because nobody really likes doing trigonometry first thing in the morning. Okay, so we can just substitute sine theta for S over L, and then we're going to get a kind of more straightforward equation for what our restoring force is. That kind of substitution, this relationship, the caveat is it's really only kind of pretty good for like angles less than about 10 degrees. If you're taking your mass and moving up to kind of really big angles and you're not kind of always keeping that string taut, and we've got to think a bit more carefully about the direction of the force, this whole situation, not so exact, but you know, for small angles like what you guys were seeing in the labs, this is a really good approximation. That's what the caveat there is. So what we're going to think about now is how can we take this restoring force and apply that kind of simple harmonic motion sort of principles to it to get the physics of what's going on here, so that we can get an equation that's going to relate, you know, our mass and our length to how long this pendulum takes to oscillate. Now, this was the relationship that you guys were testing experimentally in the lab, and we can now see a bit more, you know, about the physics of, you know, what's going on there. So let's have a look here. So we know that in this situation, our restoring force, it's equal to the mass times acceleration due to gravity times our displacement S and L, the length of our string. Now we know for any simple harmonic motion, whether it's mass on a spring or the pendulum, that the acceleration is equal to basically some constant times how much it's been displaced, so this S here. Now the algebra gets a little bit tricky here, so do take your time working this out. But what we're going to think about here is, if we know that this is the functional form of the restoring force, how can we work out what our angular frequency is for our pendulum? So we're really making that same kind of comparisons before, but we're now solving it for the pendulum. So which of these options is going to tell us the angular frequency of our oscillating pendulum? Just a quick hint with this restoring force. So you might think, okay, well, restoring force, not obviously a connection to this form of the simple harmonic motion, but remember, force is always mass times acceleration. So we can substitute this F for mass times acceleration, and then we have a mass on both sides, and we can divide that out. So that simplifies the equation for us, and it's going to make it look a lot more like that simple harmonic motion equation. So try making that substitution and then see if you can identify which one of these is the correct angular frequency for our oscillating pendulum. All right, very good. Let's see what everybody thinks for this question. Let's see what the responses are. Okay, so nobody's going for D, thinking maybe kind of could be A, or looks like a lot of people going for B, people mainly going for C. Now I can see why people might be thinking about B, because if we look at over here, we have M times G and it's over L. So I can see why you might be thinking that it could be option B. But remember that this business here, mgs over L, that doesn't equal our acceleration. That equals our force. Okay? And remember, force is mass times acceleration. So in this force here, we have a mass times acceleration, and those masses are going to cancel. So it's actually kind of very close to this option, except this mass is going to get cancelled out. So when we do that cancellation, what we actually get is option A over here. So very well done, everybody who gave that a question, especially if you spotted that it's going to be option A. Now, my kind of top tip with this one is we don't need to guess with any of these questions. Always write things out, always work through the algebra, work through the cancellations, and then you'll get it right every time, okay? But it's kind of, close to this one. Just remember, we've got to cancel that M, okay? Now, this is a really important result for thinking about the mass on a pendulum, because if we know how long our pendulum is and the acceleration due to gravity, we can work out the angular frequency, so how long our pendulum is going to take to oscillate. Now, this is nearly the exact equation that you guys were working with on Wednesday, except it's got angular frequency, and maybe we might prefer thinking about frequency or indeed time period. So for the last question, thinking about this oscillating pendulum, let's just do that same kind of bit of work that we did before. So we know the relationship between angular frequency and the length for our pendulum, and we know any angular frequency, it's 2 pi over the time period. So let's see what we get when we make this substitution. What's the relationship between the time period and the length of our pendulum? There's actually a couple of approaches you can take to this question. So you can just set them both equal and then solve for t, that's fine. Also, if we look at the options that we have here, so have a think about the things from the lab that time period depended on. So it depended on the length. Have a think, did it depend on the exact value of the mass? Maybe that might help eliminate some of these options. And also maybe think about how did the time period depend on the length? So as the pendulum got longer, what happened to the time period? Maybe if you think about that, that might help to identify which of those is going to be the correct option. All right, then let's take a look at the responses. Let's see what everybody gets for this one. Looks like we've got a kind of range of options. Looks like most people going for option A here. Okay. Now, remember that when we saw in the lab, the time period, it didn't depend on the mass. So we can actually kind of eliminate options B and C just because they depend on the mass. And also if we look here, so for our pendulum, the angular frequency is G over L, and we set that equal to 2 pi over T. There's no mass in there. So the mass kind of doesn't come into this. So we know that it's not going to be options B and C. And then we really just need to do a bit of rearranging here, and then we solve for T, okay? So what we do when we do the rearranging, we get option D over there. Okay, so just remember, so it's 1 over T, so we've got to take the inverse. Now just one last bit of physics intuition to be thinking about here. So remember what we saw in the lab. As that length got longer, the time period increased. So with option A, it's G over L. So what that would tell you is if you made your pendulum longer, the time period's going to get shorter. But we know it works the other way. So even with this question, if you felt like you didn't feel like doing the algebra, we know it's got to be option D. Okay, so very well done everybody who got option D for the pendulum over there. Now, for the last few slides for today, I'd like to share with you guys a little bit about exactly why simple harmonic motion is so important and why these are such kind of classic examples to be thinking about. And to start this, I'd like just to do a really quick recap question. So going back to that, thinking about the mass on a spring, with Hooke's law, force is equal to minus kx. Which one of these options is going to be the energy stored in that spring when we've compressed it? So with this question, maybe you can remember it from when we were thinking about the energy stored in a mass on a spring, or maybe, you know, if we look at the equation going over there, you can think, okay, how is it going to depend on the position? What might that coefficient be? Maybe you can eliminate some options there. So have a think about this. Have a chat with the people around you. Which of those options is the energy stored in the mass on a spring? All right, then, let's see what everybody thinks. What's the energy stored in our spring? Let's have a look. Okay, so people thinking it could be mainly A or C. So I think everybody's remembered it's got to be like the half kx something. But just remember, when we think about the energy, it's the half kx squared. Okay, so the correct answer is option A. Okay, so very well done, everybody, with that question. Now, we're going to see exactly why we need to kind of recap this when we're thinking about the energy stored in something. So we know for a mass on a spring, this is the energy, so a half kx squared. So let's have a think in this question. Which of these four graphs is a graph of that relationship for the energy versus the extension? So which of these graphs could be a graph of energy is equal to 1/2 kx squared? With this question, maybe you can just spot which one has to be a graph of something versus x squared. Maybe you can eliminate some, maybe you can recognize some of the other ones. So have a think about this, see which one of these is a graph of energy is equal to 1/2 kx squared. All right, then let's see what everybody thinks. Which one of these is a graph of 1/2 kx squared? Okay, nobody's going for A. Some of you could be thinking B or D. Looks like most people identified correct answer is option C. Okay, so very well done, everybody, with that question. Now, for the last couple of slides for today, I don't have any more questions, but I'd just like to share with you guys a bit why this relationship between the energy of something and the displacement which we get whenever anything's oscillating is so important in physics, and why simple harmonic motion is such an important subject in physics and just comes up again and again. So just as a bit of an example, do you guys remember a couple of weeks ago, we were thinking about nuclear physics, and we had this example of, the distance between two protons, and then we had the potential energy. You guys remember this? And if we're pushing the proton together, we're pushing it up here, it gets the repulsion, and then when it gets close enough, it snaps together and it's closely bound together. Now, this is quite a complicated relationship between the energy and position. There's a lot of stuff going on, it kind of goes up over here and it goes down over there. And the physics behind this is actually quite complicated. But we can make our life a lot simpler if we're just interested in this region around here. If we just think about this region where the two protons are really close together and there's an attractive force, then we can approximate all of this business just with that parabola. So if the two particles are just in here and they're always feeling an attractive force, we can use that simple harmonic motion approximation, and that makes our life a lot simpler. Now, clearly, it doesn't work if we get over here, we get into the kind of Coulomb's law, and over here, it's kind of not exact, but it's pretty good. It's a pretty good approximation, and it makes our life so much simpler. So that's just one example from nuclear physics, but this principle comes up again and again, that any time we're at what we call a minimum of the potential energy, we can approximate it with a parabola, and then we can model the whole thing with those simple harmonic motion equations that you guys have just worked through. So I'll just share with you guys just a couple of quick examples here. So maybe we're thinking about the forces between an atom. So in the atomic scale, again, we have this kind of business where there's some repulsion, but there's a potential minimum. Now, who gave the challenge question a go this week on Tuesday? Who was thinking about that with the curve sketching? Yeah, so these are the curves that you guys were actually sketching on Tuesday. So they're actually graphs of potential energy versus distance in orbits about a black hole. So whether we think about atoms or black holes, we get this potential minimum business. And the whole physics there can be quite complicated. But we can simplify it a lot. You know, we can just put a little parabola there at the minimum. And over here, you know, we've got this whole thing from general relativity. Maybe you guys might learn about that towards the end of your degree. But we can make our life a whole lot more simple if we just take this minimum and we replace it with a little parabola. So whenever we have anything close to a minimum and it's just kind of oscillating around, we can just use those equations that you guys worked through for simple harmonic motion, whether we're thinking about black holes or atoms or nuclear physics. We can always approximate it with simple harmonic motion. So the very last slide I'd like to share with you guys for today is, you know, we had that little picture last week from Twitter, you know, physicists, absolutely anything. Is this a simple harmonic oscillator? So I hope you guys, I've convinced you guys that this could potentially be a simple harmonic oscillator. And actually, I don't know if they realize, but a butterfly is actually a really good example because you could actually approximate that with a little simple harmonic oscillator. That would actually work quite well. So excellent work today with all those equations. Just a quick couple of reminders for next week. In a change of form, there's no bank holiday on Monday. I know it's kind of, we all got kind of used to that. So no bank holiday. We're going to have the lecture as usual on Monday. And on Tuesday, we're going to have the workshops as usual. I'm just going to say a bit at the beginning of kind of exam prep stuff, what to expect, and some tips, all that good stuff, okay? So I hope you guys have an excellent weekend, and I'll see you guys all on Monday.